Good afternoon. This is Professor Muhammad Ashraful Alam, and today we'll be discussing reliable sensing with unreliable sensors. You see, in the computers or solar cells or wearable or implantable sensors, they actually function very differently in the traditional controlled environment that people are typically used to versus those that are used in the wild when they are exposed to the elements of the nature. For a sensor in the lab, it is possible to control the temperature and the reference condition so that by measuring the potential psi of the sensor, one can determine the analyte concentration N. In the wild, temperature and the reference conditions are unknown. So the question is, how do you get reliable signal from this unreliable measurement? The way we proposed to solve this problem is a fundamental rethinking about the sensor. Instead of thinking about sensors just as an electronic device, we may think about a sensor as a noisy communication channel. Here, the message that we want to send is the analyte concentration, and the message received is the voltage signal psi. So the question is, in that case, we would be able to take various concepts from communication theory, classical communication theory, in order to solve this problem of ambient variables that are uncontrolled and noise that are invariably included in this sensor configuration. So one of the first strategy from the communication theory that we can use is this notion of self-calibration through differential measurement. Consider two sensors that are slightly different and therefore they have a slightly different response. The only reason that happens to be so is because their reference concentrations are different. But the interesting thing is that if you take their difference and make a differential measurement, then it is possible to calculate the temperature T. As you can see from here, psi 1 and psi 2 are the two measured values, but the delta psi acts like a thermometer, which is perfectly replicates the ambient temperature. So the idea here is that if you have an unknown temperature T, if you have an unknown analyte concentration, your measured psi is difficult to deconvolve. And to do so, what you do is then take two slightly different sensors. Their difference, measured their difference, which gives you the temperature T. Once the temperature T is known, then you can predict the concentration perfectly without the effect of, after having taken out the ambient variable of the. The second approach is this strategy of eliminating fake news or fake news detection algorithms used by Facebook and Twitter. And the idea here is assume that there is some reference concentration, round truth, but the four sensors that are being used, some of them are bad to begin with, while others become reliable and noisy, reliable and unreliable as time passes. If you try to take an average or try to take a majority voting, they will not really work very well. Instead, if you use a Bayesian MLE, which will give you the averaging based on the historical credibility of the sensors, that will give you a much better estimate of the unknown analyte concentration. And this is something we have demonstrated by a 3-month-long experiment where a set of 6 sensors were irradiated by gamma ray, thereby causing and therefore having drift in the measurement as they are making different measurements, and this drift is reflected and plotted in here. But what you can do using that algorithm, fake news detection algorithm, what you can detect is which of those sensors, 6 sensors, are gradually becoming unreliable due to the gamma irradiation, and then take them out if you wanted from making the measurement or try estimating the ground truth. So here you rely, instead of 5 or 6 the sensors, you rely on the 3 reliable one and exclude the unreliable ones. But it turns out, because the drift of the gamma irradiated ones are systematic, so therefore in fact you can correct for the drift, and in that case can make all the sensors, despite their variability, despite their drift, a reliable estimator of the ground truth. And this has a dramatic implication in terms of the energy needed for communication that you will hear in other talks. For example, because you are no longer sending out fake news from the from the unreliable sensors, therefore the amount of energy needed for communication and for signal processing is dramatically reduced. And in fact, with a few reliable sensors, even 1/10 of the original sensors are reliable, it turns out this algorithm allows us to export that or send that information reliably over this noisy. So overall, the approach that I discussed here today is a novel and fundamentally new capability that I think would apply to all wearable and implantable sensors, as well as other electronic devices working in the wild, such as solar cells, integrated circuits, and so on. Thank you.